Good morning, everyone. Welcome to today's class. We are dealing about separation axioms. In previous class, we have seen what are the separation axioms, namely T0, T1, T2, T3, T4. And the previous class, we have discussed what is Zetikno space, that is T3 and a half space, and some of its properties. In today's class, we will discuss about the compactness and separation axioms. Remembering that a space is said to be compact if every open cover of that space should have a finite subcover. Now, suppose we have a host door space. Suppose we have a host door space X. This means that any two distinct singleton subsets, say X and Y, of X can be separated from each other by disjoint open sets. Nothing but the definition of a host door space. Now suppose we have given singleton set Y by a finite subset F. So X is there and a finite subset F is there. Suppose F is equal to 1, 2, 3. So F is equal to 1, 2, 3, and you are having an X separately. Since the space is horsed off, you take your X and 1, you will get open set covering X and one open set covering 1. We should be we should be disjoint one. So you can take X and 1. So specifying here means you're having one X here. This is your X, and suppose you are having the elements, some are finite elements, something like this. See, this is a finite element. Since this is horsed off, you will have an open set containing X and an open set containing this one. And similarly, when you're taking open set containing X, means you will get another open set containing this one, because this point and your X are different. And similarly, you can have some open set containing next element, and you have some open set containing this element and this. Now if you're having a finite set and X, again you can go for two disjoint open sets. This one is contained in X and another this finite set is contained in the other open set. Namely, you can take this as for each one. See here, for I is equal to 1, 2, 3, etc. up to n, ui and vi. So you can select open set such that x belongs to ui and yi belongs to vi, with the condition ui intersection vi is empty. Now if you're taking u as intersection of such ui's, so when you're taking intersection, evidently it belongs to x. Belongs to x. Since x belongs to each ui, when you're taking the intersection, it evidently belongs to I. Now for a neat picture means go for, see, suppose this is here x, so x is there and this is here point some y. I'm taking only some 3 element set, so y, z, and another number is A. These three are different from your X. Since your space is a Hausdorff space, you can have, first you will take X and Y. So you have some open set containing X and an open set containing Y, which is different from, this is your first case U. I will name this as, this is your UI. So this is your UI and this is your VI. Okay. Now if you are having another point X and Z, so here you can again have some open set. See, again you will have some open set containing X and an open set containing Z. So in this case, this is your U1, first I should mention. So this is your U2. So read this as U1, this is U2. Now this is V1, now this is V2. Okay, now we are having X and A. Again, two separate elements. So we can go for another open set such that this X containing X. So this is my open set U3, and here I am having another open set which containing A. So this is my V3. So I have taken two element sets and have got like this. Now you can define what is capital U. Capital U is intersection of U1, U2, U3. Now definitely it will contain X. And V as union of these V1, V2, V3. Then that will have all your elements Y, Z, A. Then clearly U and V are open sets since we are taking the finite union and finite intersections. Open sets, and X belongs to U and F is contained in V, and U intersection V is empty set. So here in a Hausdorff space, if you're having a point and a finite set of elements, we can separate them. 2.1 proposition: X be a Hausdorff space and X belongs to X, and F a compact subset of X not containing X, then there exist some open sets U and V such that X belongs to U and F is contained in V, and V intersection U is empty. So here is, previously we have considered F as a finite set. So here we are considering F as a compact set. So compact means every open cover should have a finite subcover. Since F's members is very simple, it means we are using the previous fact. For each Y belongs to F, there exists open set Uy and Vy. Since we can take X belongs to Uy and Y belongs to Vy, and Uy intersection Vy is empty since the space is going to be a Hausdorff one. Now take the family Vy, Y belongs to F. Now this family is an open cover of F since each Vy is open. Now since F is compact, this should have a finite subcover. So say that finite subcover is Vy1, Vy2, extra Vyn. Now we can handle this in the same case as in the previous one, that means the finite case. So we can take the open set U as intersection of all Uy's and V as union of all Vy's. Then U and V are disjoint open sets and X belongs to U and F is contained in V. Now 2.2 corollary. A compact subset in a Hausdorff space is closed. I repeat, a compact subset in a Hausdorff space is closed. So suppose X is a T2 space, that is a Hausdorff space, and F is compact. What we want to prove is F is closed. Then, by proposition above, for any X belongs to X minus F, that means X and F are separated. There exist open sets U and V such that X is in U and F is contained in V, with the condition U intersection V is empty. Since U intersection V is empty and F is contained in V, in particular we have U intersection F is empty. Hence, F is not a member in U. That means U is contained in X minus F. U is contained in X minus F. Thus, X minus F is a neighborhood of each of its points. Why? Because you have taken an X and U is an open set which containing X. Now you have got in X minus F, X belongs to X minus F. So each point of X minus F has a neighborhood inside your set X minus F. That means X minus F is a neighborhood of each of its points. That means X minus F is open. So F is closed. So the result, a compact subset in a Hausdorff space is closed. 2.3 corollary. Every map from a compact space into a T2 space is closed. Every map from a compact space into a T2 space is closed. Next, the range of such a map is a quotient space of the domain. That is, here we are having two sets. Every map from a compact space. So this is compact and this is T2. Now what we want to prove is this map is closed. That means you take here one closed set and prove that its image over here is also closed. So this thing we want to prove. So suppose f from x to y is a continuous where x is compact and y is Hausdorff. So this is your x and this is your y. Yes. Let C be a closed subset of X. So this is you are taking as your closed subset C. Then C is compact. Yes, we have studied that a closed subset of a compact space is compact, or compactness is weakly hereditary property. And so f of C is compact because a continuous function will map a compact set to a compact set. Okay, so f of C is closed in Y by above corollary. Above corollary says that a compact set is closed in a Hausdorff space. So here you have got a closed uh, set in the Hausdorff space. Then by using previous corollary, this is closed. For the map F is closed. So the map F is closed. I repeat the proof. You have taken X as a compact space, Y as a T2 space. Now from X you have taken a closed set, and since this is closed, a closed subset of a compact space is compact, this C is compact. Now we take this continuous image. A continuous image of a compact set is compact. So here you will get a compact space. In T2, by previous corollary, a compact space is closed. Therefore, this is closed. So image of this closed set is closed. Therefore, F is a closed map. Now we want to prove that the range of such a map is a quotient space of the domain. For that we should remember the previous chapter result. Every closed surjective map is a quotient map. Every closed surjective map is a quotient map. Now we have got this map is closed. Only thing is to show that it is surjective. In order to get the surjective idea, we will use set be the range of f. Now you define f as a map from x to z. That means the range of f. Then evidently it should be an onto map. So an onto closed map should be a quotient map, and consequently z is a quotient space of x by definition. Now in your notes, this is 2.5 corollary, but 2.5 corollary, in order to prove this, we need 2.4 corollary that is missing, and that can be found in the next page. So this is the 2.4 corollary. This corollary says that a continuous bijection from a compact space into a host-row space is a homomorphism. That is, a continuous bijection from a compact space into a host-row space is a homomorphism. So f from x to y be a continuous bijection where x is compact and y is host row. We claim that f is open. So in order to prove that it's a homomorphism, we want to prove that f is open. Let G be an open set in X, then X minus G is closed. Therefore, f of X minus G is closed. Then by using corollary 2.3. Now find what is f of X minus G. Since it is bijection, f of X should be y, and this is y minus f of G. Since y minus f of G is closed, f of G is open. Hence f is continuous, open bijection, and hence it is a homeomorphism. So it is a homeomorphism. In order to prove that it's a homeomorphism, we want to prove that f is a bijection and f inverse are continuous. So here we have proved that f is open. F is open directly implies that f is continuous. So in 2.4 corollary, we have proved that a continuous bijection from a compact space onto a host row space is a homeomorphism. Now come back to 2.5 corollary. Every continuous one-to-one function from a compact space into a host row space is an embedding. So before going for this corollary, we should see what is an embedding. An embedding of a topological space X to a topological space Y, we mean a one-to-one function f from x to y such that if we consider it as a map into f of x, that is range of f, that is a homeomorphism onto this subspace of y. That means embedding is nothing but a map f from x to y, which is 1 1, and when we restricted this map to range of f, if we are getting a homeomorphism, then we'll say that this map is an embedding. Now proof is very immediate. from the corollary 2.4. Since 2.4 says that a continuous bijection from a compact space onto a Hausdorff space. So here we are restricted that to the range of f means exactly you are having an onto map. So the remaining conditions are the same. So you can say that that is an embedding. So application of this corollary is first application. We know that there is no continuous one-to-one map from the unit circle onto the real line. So if f were such a map, suppose f is such a map, then f of s dash would be homeomorphic to s dash. Then by the corollary, s dash is compact space. Then f of s dash would be compact with continuous image of a compact space, comma compact and connected subspaces of R, where f of s dash must be closed bounded interval. But such an interval cannot be homomorphic to s dash. Reason is the interval has a cut point, whereas the unit circle has no cut point. Cut point means if you are removing that point from the set, you will get a disconnected set. Now, second application, if X is any set in a compact topology on X, that is topology on X which make it a compact space, that means the compact topology cannot be properly stronger than a host of topology. If X is any set, then a compact topology cannot be properly stronger than a host of topology. For doing this, suppose tau1 and tau2 are topologies on X such that X tau1 is compact and X tau2 is host of. Now we want to prove that tau1 is weaker than tau2. That is, tau1 is contained in tau2. Now suppose the other way inclusion. So if tau1 is contained in, tau2 is contained in tau1, then the identity function you can consider from x to x, that is tau1 tau2 continuous, and hence a homeomorphism by corollary 2.4. So what you will get is tau1 should be equal to tau2. Now as a note you can have from this result, in a class of all compact topologies on a set, every host of topology is maximal, and that in the class of all host of topologies on a set, every compact topology is a minimal one. That is, if you're taking a collection of compact topologies on a set, then every host of topology is a maximal element, and in the class of all host of topologies on a set, every compact topology should be a minimal element. See, this we have stated previously, but we haven't proved. So prove that topology's sine curve X is not path connected. So remember the definition of topology's sine curve. Here X equal to A union B, where A is equal to set of all X comma sin 1 by X belongs to R2 such that 0 less than X less than or equal to 1, and B as set of all 0 Y belongs to R2 such that minus 1 less than or equal to Y less than or equal to 1. And we want to prove that this is not path connected. There is no path in X from. For that we will pick 2 points. One point is 1 comma sin 1 and another point is 0 0. And our claim is that there exists no such path from 1 comma sin 1 to 0 comma 0. If possible, let alpha be such a path. Now, y be the range of alpha. Then y is compact. Reason is closed interval alpha is defined from closed interval 0, 1. So closed interval 0, 1 to anything, and you take f of that means it should be, since closed interval 0, 1 is compact, continuous image is also compact. And again connected. Closed interval 0, 1 is connected, so it is connected subset of X and contains the points 1 sin 1 and 0, 0. Then Y should contain the entire set A, because if a point B, sin 1 by B is not in Y, then the set xy belongs to Y such that X is greater than B, and xy belongs to Y such that X less than B will give the disconnection of Y. Then Y must contain the entire set A. If this is not true, then we can find a B such that will separate your Y. But you have seen that Y is compact and connected. So such a way is not possible. Therefore, Y must contain the entire set A. Thus A is contained in Y. A is contained in, and Y is compact. So Y is compact, hence closed in X. So A closure is contained in Y. Now since A you are taken as a dense in X, it follows that Y should be equal to X. Since dense means A closure should be equal to X. But you have seen that A closure is contained in Y. So Y should be equal to X. That is Y you are taken as the range of alpha. So alpha is onto. Since alpha is onto the corollary 2.3, X is a quotient space of the unit interval 0, 1. So X is a quotient space of the unit interval 0, 1. It is a contradiction, since every quotient space of a locally connected space is locally connected. Since closed interval 0, 1 is locally connected, why X is not so? Thus, it is not path connected. So there exists no path in X joining 1, sin 1 to 0, 0. That is, it is not path connected. Now 2.6 theorem. Every compact Hausdorff space is a T3 space. Every compact Hausdorff space is a T3 space. T3 space means the space is T1 and regular. Regular means if you are having a point and a closed set not containing that point, then you can able to find two open sets such that that point belongs to the open set U, and the closed set is completely contained inside another open set V, and U intersection V is empty. So here we want to prove that every compact Hausdorff space is a T3 space. So let X be a compact Hausdorff space. Then every closed subset of X is compact. And so the space X is regular by proposition 2.1. Since X is also T2, it implies it is T1. Thus X is a T3 space. Remembering 2.1, proposition 2.1? Proposition 2.1 says that see, X Hausdorff space and F is compact subset of X not containing X, then there exist open sets U and V such that X belongs to U and F is contained in V. This is nothing but the condition for regular. So here we have proved that every compact Hausdorff space is a T3 space. Next proposition 2.7. Let X be a regular space, C a closed subset of X, and F a compact subset of X, such that C intersection F is empty. Then there exist open sets U and V such that C is contained in U and F is contained in V, and U intersection V is empty. That means we have replaced your point with an irregular space with a closed set and a compact subset. The two are disjoint ones. And we can have this proposition in the next class. Just do note that such a proposition is there. Okay. Thank you. If you're having any doubt, please free to ask or post below this video. Thank you. Thank you for your patient listening.